Hello everybody, welcome back. Today we'll talk a little bit more about how to compute Fibonacci numbers. And in particular today what we're going to do is we're going to show you how to produce a very simple algorithm that computes these things correctly. On the other hand, we're going to show that this algorithm is actually very slow and talk a little bit about how to analyze that. So let's take a look at the definition again. The 0th Fibonacci number is 0, the first Fibonacci number is 1, and from thereafter each Fibonacci number is the sum of the previous two. Now, these grow pretty rapidly, and what we would like to do is have an algorithm to compute them. So let's take a look at how we might do this. Well, there's a pretty easy way to go about it, given the definition. So if n is 0, we're supposed to return 0, and if n is 1, we're supposed to return 1. So we can just start with a case that says if n is at most 1, we're going to return n. Otherwise, what are we supposed to do? Otherwise, we're supposed to return the sum of the n minus first and n minus second Fibonacci numbers. So we can just compute those two recursively, add them together, and return that. So this gives us a very simple algorithm, 4 lines long, that basically took the definition of our problem and turned it into an algorithm that correctly computes the thing it's supposed to. Good for us. We have an algorithm and it works. However, in this course, we care a lot more than just does our algorithm work. We also want to know if it's efficient. So we'd like to know how long this algorithm takes to run. And as sort of a rough approximation to this, we're going to let t of n denote the number of lines of code that are executed by this algorithm on input n. So to count this is actually not very hard. So if n is at most 1, the algorithm checks the if case, goes to the return statement, and that's 2 lines of code. Not so bad. If n is at least 2, we go to the if case, we go to the else condition, and then run a return statement. So that's 3 lines of code. However, in this case, we also need to recursively compute the n minus first and n minus second Fibonacci numbers. So we need to add to that however many lines of code those recursive calls take. So all in all, though, we have a nice recursive formula for t of n. It's 2 as long as n is at most 1. And otherwise, it's equal to t of n minus 1 plus t of n minus 2 plus 3. So a nice recursive formula. Now, if you look at this formula for a little bit, you'll notice that it looks very similar to the original formula we used to define the Fibonacci numbers. Each guy was more or less the sum of the previous two. And in fact, from this you can show pretty easily that t of n is at least the nth Fibonacci number for all n. And this should be ringing some warning bells, because we know that the Fibonacci numbers get very, very, very large. So t of n must as well. In fact, t of 100 is already 1.77 times 10 to the 21, 1.77 sextillion. This is a huge number. Now, suppose we were running this program on a computer that executed 1 billion lines of code a second. It ran at 1 gigahertz. It would still take us about 56,000 years to complete this computation. Now, I don't have 56,000 years to wait for my computer to finish. You probably don't either. So this really is somehow not acceptable if we want to compute Fibonacci numbers of any reasonable size. So what we'd really like is we'd like a better algorithm, and we'll get to that next lecture. But first, we should talk a little bit about why this algorithm is so slow. And to see that, maybe the clearest way to demonstrate it is to look at all of the recursive calls that this algorithm needs in order to compute its answer. So if we want to compute the nth Fibonacci number, we need to make recursive calls to compute the n minus first and n minus second Fibonacci numbers. To compute the n minus first, we need the n minus second and n minus third. To compute the n minus second, we need the n minus third and n minus fourth. And it just keeps going on and on from there, and we get this big tree of recursive calls. Now, if you'll look at this tree a little bit closer, it looks like we're doing something a little bit silly. We're computing fn minus 3 separate times in this tree. And the way that our algorithm works, every time we're asked to compute it, since it's a new recursive call, we compute the whole thing from scratch. We recompute fn minus 4 and fn minus 5 and then add them together and get our answer. And it's sort of this sort of computing the same thing over and over again that's really slowing us down. And to make it even more extreme, let's blow up the tree a little bit more. Fn minus 4 actually gets computed these 5 separate times by the algorithm. And as you keep going down more and more and more times, are you just computing the same thing over and over again? And this is really the problem with this particular algorithm, but it's not clear immediately that we can do better. So come back next lecture and we'll talk about how to get around this difficulty and actually get a fairly efficient algorithm.